to minimize GTV minimization, you need to take into account that there are two parts. So there are two parts in GTV minimization. The first is the local loss function, or the sum of local loss functions, and the second part is this TV minimization. So it would be much easier, or the minimization of this objective function would be much easier if there would not be these coupling terms, if these coupling terms would go away. And so the idea now is, one way to make them go away is just to hold the model parameters at all nodes except one fixed. So you hold all model parameters at all nodes except node I fixed, and then optimize only with respect to the model parameters at node I. So this is like something like block coordinate descent or coordinate descent, iterative coordinate descent. And I believe many of you have come across this idea, this optimization idea in a course on linear algebra, on numerical linear algebra, because this is the same idea as in the Jacobi method for solving linear equations. How many of you have heard about the Jacobi method for solving linear equations or linear systems? Yes, at least some. And maybe another method that you have heard about is called Gauss-Seidel. Gauss-Seidel is another iterative method for solving linear equations. But maybe the most simple one is the Jacobi method. And the idea is get rid of coupling in an optimization problem or in an equation by assuming you know already most of the variables. So you have solved already most of the variables except one. And then you find the solution for this one variable. And then you repeat this process for all other variables. So you hypothesize, or you just assume, I have now found all the optimal choices for all model parameters except at node Wi. So what should you do now? Well, you optimize this objective function only with respect to Wi. And this becomes very easy because then there's no coupling anymore between optimization variables, but there's just a quadratic term in this one optimization variable, Wi. And this becomes then quite easy to solve. So, and this is the resulting algorithm. So you start again with some initial choice at each node I, and you compute this update here for Wi. So this is again, it's actually a proximal step or a proximal operator. And this proximal term includes the current estimates or the current local model parameters at all neighbors. So again, we have this pattern, this algorithm pattern. You have to exchange model parameters between the neighbors, and each node then uses the model parameters of its neighbors to compute an update, to improve its own local model parameters. And here in this algorithm, we do it by using this penalty term given by the sum over all neighbors. So this seems very natural. So we want to minimize the local loss function, but also we want to ensure that the local model parameters at node I are not too far away from the current local model parameters at the neighbors. Yeah, and it's a nice exercise. You can write out this, or you can reformulate this sum here as another penalty term, which is without the sum. So you just have Wi and some, let's call it W tilde. And this W tilde is exactly the average of all the neighbors' model parameters. So you can replace this term here with this alpha times the squared Euclidean distance of this optimization variable, which is the model parameters at node I that we want to update, minus the current average over the neighbor model parameters. So I might, if I don't have this already as an exercise in the lecture notes, I will add this as an exercise immediately to show that this term, this sum here is actually the same as this squared Euclidean norm of the difference between Wi and the average over all neighbors. And yeah, by the way, this is again nothing but a regularized training problem. It's again a ridge problem, a form of ridge regression, using a specific penalty, or using a shifted penalty term. In ridge regression itself, you have you minimize the training error, the MSE of the current weight vector, plus the regularization parameter and the squared Euclidean norm. So this is ridge. And here in this FedRelax algorithm, federated learning algorithm, we use not the squared Euclidean norm of the model parameters, but of the difference between the model parameters and some other parameter vector, which is the average of the neighbors' model parameters. Wow. Let me get rid of this painting. Yeah, there have been some questions. So if I got correctly, the main difference between FedProx and FedRelax is that FedProx considers all clients while FedRelax only the neighbors. Yes, very good comment. So the difference between FedRelax and FedProx is that FedProx learns the same model parameters for all nodes. So FedProx is an algorithm for the single model federated learning setting. So this is one of the main flavors I will talk about next week. This is related to FedProx. In FedProx, we want to learn one set of model parameters or global model parameters, but we share it then with all the clients. And in FedRelax, we learn different model parameters at all nodes. So this is a fully distributed, decentralized federated learning algorithm. If alpha is large and the network is well connected, then we might up also with the nearly identical model parameters. But in general, it will not be always the same model parameters at the nodes, depending on the cluster structure of the network. So FedRelax is for decentralized or personalized federated learning, where every node has a potentially different model parameters. On the other hand, FedProx is an algorithm for single model federated learning. So you want to train one model from local data sets, and this one model is then, or the model parameters for this global model is shared with all nodes. Okay, and yeah, I just want to point out here in this FedRelax that this allows very intuitively or very naturally to generalize to non-parametric models. As I said, we just need a way to extend or to reformulate this penalty term here, this variation term for non-parametric models. And one way to do this, as you have tried out in the first assignment, is to use the squared differences between the predictions on a test set. So we can compare two decision trees, for example, by comparing their predictions on a test set. And we say two models are similar if they deliver approximately similar predictions on a test set. And yeah, by the way, this also means that the models at different nodes are not necessarily all decision trees. They only need to have the same value range in their predictions. We need to be able to compute this squared difference. But this hypothesis here on node I could be, for example, a decision tree, while this hypothesis at node I prime could be a deep neural network, which also outputs a numeric quantity. So they can be completely different models at different nodes. They only need to have the same value range in their output, in their predictions. For example, they all need to be regression models. They need to output numeric quantities that we can compare. But the model itself can be completely different at different nodes.